Do LLMs benefit from their own words? By researchers Jenny Y. Huang, Leshem Choshan, Ramona Studio, Tamara Broderick, and Jacob Andreas from MIT and IBM Research.
If you're building multi-turn LLM chat applications right now, your default setting is almost certainly to pass the entire conversation history, including every single one of the assistant's own past responses, straight back into the context window. This paper proves that this default design choice might be a massive waste of compute. By completely omitting the assistant's past responses, a strategy they call assistant-omitted prompting models often maintain or actually improve their response quality. Doing this reduces your cumulative context length by up to 10x. The reason: keeping the model's past responses often causes context pollution. Your models are overconditioning on their past outputs, and they end up, carrying forward bugs, hallucinations, or stylistic artifacts into future turns.
Okay, take a breath. Welcome to this breakdown for the AI Paper podcast series. If you're an ML builder, an AI researcher, or really just someone trying to optimize token usage in your apps, you really need to care about this.
Absolutely.
We're talking about saving latency, cutting massive token costs, and counterintuitively simultaneously making your model's outputs better.
Yeah, it feels like a free lunch.
Right, which is something we know rarely exists in machine learning. So let's really unpack this. How did the MIT and IBM researchers prove that throwing away a model's own words is actually a benefit?
Well, they set up a highly controlled experiment, but what gives this paper so much weight is that they refused to rely on synthetic benchmarks.
Ah, nice.
Yeah, they went straight for real-world in the wild chat logs. They pulled from the wild chat and ShareLM datasets, and they specifically filtered for complex technical conversations.
So we're talking about human-to-LLM interactions involving, advanced math, deep coding sessions, system debugging.
Exactly. And to make sure the findings weren't just some strange quirk of a specific architecture, they tested this across a whole spectrum of models. 4 different ones, actually.
Right. They use smaller open reasoning models like Cum3-4b and DeepSeek R1 Distill Llama 8b, right?
Yep. And then scaled up to a mid-size GPT OSS 20b, all the way up to the frontier model, GPT 5.2.
The experimental setup itself is beautifully simple. They ran these multi-turn conversations through the models using 2 different configurations. The first one is the industry standard full context, or FC. You feed in the user prompt, then the assistant response, then the next user prompt, the next assistant response, just over and over.
The standard loop.
All right. But the second configuration is where the magic happens. They call it assistant omitted, or AO. In the setup, every single past assistant response is stripped out.
Just completely gone.
Yeah, it's literally replaced with a tiny placeholder bracket that just says response provided.
And that placeholder is crucial. It keeps the alternating user assistant turn structure intact.
Oh, I see. So the model still understands that a conversational turn occurred.
Exactly. It knows it spoke,
Yeah.
but it is completely blind to the actual words it generated in the past. After generating the new responses under both conditions, they use GPT-5 as an LLM judge to compare the outputs turn by turn.
Let's talk about the raw infrastructure impact first, because for anyone dealing with KV cache limits, the context length revelation here is wild.
It's a fundamental shift in how we think about scaling. Just a quick refresher, the KV cache is that massive memory bottleneck where you're storing all the key value states for every single token to keep the context window open for the user.
And it gets huge.
Well, it's terrible. The paper shows that by round 8 of a typical technical conversation, full context histories bloat to anywhere from 25,000 to 55,000 characters.
Wow.
And that scaling is linear and incredibly aggressive.
Meaning your inference costs and your time to first token are degrading with every single message the user sends. You're basically being punished for having a long conversation.
And it gets worse if you're self-hosting, because that bloat eats up VRAM that you could be using to serve concurrent users. But look at the assistant omitted context. Because you're only storing the user's prompts in those tiny placeholder brackets, the context length stays nearly flat.
Right, because you're dropping chunks of text.
Yeah, massive chunks. By round 8, it's only consuming about 5,000 to 10,000 characters. We're looking at a 5x to 10x reduction in context usage.
That's insane.
It isn't just a marginal optimization. It completely changes your infrastructure overhead.
But this is where it feels completely counterintuitive. I mean, how can the model possibly answer correctly if it can't remember what it just said?
Think about human interaction. If I'm talking to you and I completely erase your memory of the last sentence you just spoke, you're going to struggle to keep up.
I'd be totally lost.
Right. So why doesn't the LLM just crash and burn?
Because we anthropomorphize these systems. We assume multi-turn conversations inherently require multi-turn memory. We think memory works like human memory, but for an LLM, it's just a sequence of tokens.
Okay, fair point.
When the researchers analyzed how humans actually prompt models in the wild, they found that true multi-turn dependence is surprisingly rare. They categorized the mid-conversation prompts into 3 distinct buckets, and the data shatters the myth that models constantly need to see their own past work. The breakdown of those prompt categories blew my mind. Let's walk through how users actually talk to these models. The largest chunk of mid-conversation prompts, about 36.4%, are just completely new asks.
Right. Over a third of the time, the user is just treating the chat window like an endless whiteboard.
Yeah.
The paper gives a brilliant example of this. A user asks the model to describe an unmade Christopher Nolan film. The model generates a long, complex response about time dilation or whatever. Then, in the very next turn, the user types, outline an unmade Wes Anderson film.
The model absolutely does not need to read its Nolan script to write the Anderson one. It's starting a totally new task. Storing that massive Nolan response in the context window is purely wasted compute.
Right.
It provides zero signal to the new prompt and only adds noise.
It's the ChatGPT effect. Users just erase and start over mentally, but the model is secretly hoarding all those old scribbles. Now, the next major category of prompts involves follow-ups with feedback. This accounts for about 30.5% of prompts. These are situations where the user is refining a previous answer, but they provide concrete, actionable constraints in the new prompt.
The paper highlighted a great conversation about a server setup to illustrate this, didn't it?
Yeah, the NAS disk topology example. A user lists out 17 different hard drives. They've got 18 TBs, 14 TBs, a whole mix, and they ask the model for a true NAS server design.
Right.
The model spits out a topology. Then the user replies to that output saying, prevent any data loss. My priorities are redundancy and space efficiency.
And if you think about how attention mechanisms work under the hood, the model doesn't need its old, flawed NAS design to fulfill that second prompt.
Not at all.
To write a better response, it just needs the user's first prompt, which contains that raw list of 17 drives, and the new constraints from the second prompt, which prioritize redundancy.
It can generate a much better, fresh design from scratch using just the user-side history. Attending to the previous assistant response is totally redundant and potentially distracting.
So if you add up those first 2 categories, the completely new asks and the follow-ups with fresh constraints, that's roughly 66% of the time.
Yeah, 2/3.
2/3 of our prompts absolutely do not need the model's past responses. We are basically paying a 100% tax for a feature we only truly need a third of the time.
That remaining third, 33.1% to be exact, is the category of follow-ups without feedback. This is when a user types something lazy like, the second one is not working, or reflect on your response.
Right, the ambiguous ones.
Exactly. If the user just says, the second one is wrong, the model obviously needs to look at its past response to know what the second one actually refers to. That is the only scenario where full context is truly required.
Okay, so we're undeniably wasting compute for the vast majority of a conversation. But is there an actual penalty to the output quality, or is it just a server cost issue? Like, if the model sees its old output, couldn't it just ignore it if it's not relevant?
It rarely ignores it.
Yeah.
Seeing its past responses can actively sabotage the model. This is the concept of context pollution.
Context pollution.
Yeah. Context pollution happens when a model anchors too hard on its previous text. Because it generated those tokens, it trusts them implicitly. It gets pulled towards its own previous tokens rather than reasoning purely about the new requirement.
It's biasing itself.
It essentially brainwashes itself, propagating early errors, hallucinations, or stylistic quirks across the rest of the conversation.
The paper mentioned some wild examples of this context pollution from the real-world data. Didn't they look at a coding scenario involving data clustering to show how parameters leak across turns?
They did, and any developer listening will instantly recognize how painful this is. A user asks GPT 5.2, the frontier model, to write some clustering code using UAMA.
Okay, standard task.
The model does it correctly, and it includes a specific parameter, metric Jacquard, which is totally valid for a UAMA implementation. 2 turns later, the user changes their mind. They type, use TSNE instead.
Which is a totally normal developer workflow. You
Right.
try one algorithm, you don't like the visual clustering, you swap it for another.
Exactly. Yeah. But look at what the full context model does. It rewrites the code for TSNE, but it carries over that metric Jacquard parameter because it was sitting right there in its previous response.
Oh no.
Yeah, that parameter acts as a local attractor in the model's attention space. The problem is, that metric is completely incompatible with scikit-learn's TS&E solver. The model introduces a hard bug just because it couldn't let go of its past output.
Meanwhile, the assistant omitted model, which is completely blind to its past UAP code, just looks at the prompt use TS&E instead, alongside the original data constraints.
And it writes flawless, standard TS&E code. It doesn't have the distraction.
That's fascinating.
And exactly that mechanism applies to hallucinations as well. They found a fascinating case with Qwen 3. A user asks it to write a paper about novels featuring child narrators. The model hallucinates wildly. It claims that The Bell Jar and The Handmaid's Tale have child narrators.
Which, for the record, they definitely do not.
Far from it. Then, in a later turn, the user asks the model to generate a polished abstract for the paper. Because those hallucinated examples are sitting in the full context window, the model just blindly copies those exact wrong book titles into the new abstract.
It treats its own past hallucination as grounded fact.
Yep. But the assistant omitted model generates a fresh abstract from scratch. Since it isn't anchored to the bad examples it wrote previously, it correctly references actual books with child narrators, like Huckleberry Finn.
Wow.
It fixes its own hallucination simply by being forced to rethink the problem from the user's base prompts.
It's not just hard bugs or factual hallucinations either. There's also a phenomenon they call stylistic inertia.
Oh, I love this one.
Right. The model gets trapped by its own formatting. A user asks Qwen 3 how to call nested Python functions. The model decides to write this massive, verbose, multi-part tutorial with code blocks and bullet points everywhere. Then the user prompts, reflect on your response.
It's almost like when you start writing an email in a super formal tone, and halfway through you want to be casual, but you look at your first paragraph and feel obligated to keep using words like furthermore. The LLM is doing the exact same thing.
That is a perfect analogy. A true reflection would require a metacognitive shift in tone. But the full context model looks at its massive tutorial, gets trapped in that stylistic inertia, and instead of actually reflecting, it just generates another massive Python tutorial that repeats the exact same points.
It cannot break out of the stylistic pattern it established.
Exactly. The assistant omitted model, free from that visual anchor, actually attempts a standard, concise reflection.
There was one more example that really stood out, involving a math formula. It showed how a model can actually get confused by its own notation.
Oh yeah, I remember this.
Yes, this involved DeepSeek R1 and a conversation about LLM temperatures. In an early turn, the model creates a Boltzmann-style formula, but it writes it with the symbol theta in the numerator. In this specific, slightly unusual parameterization, a higher theta means a sharper distribution. It's acting as an inverse temperature.
Okay, so it establishes a weird baseline.
Then in the very next turn, the user asks how temperature affects output diversity. The full context model looks back at its own formula involving theta, gets totally confused by its own non-standard notation, and completely reverses the standard explanation of LLM temperature.
Unbelievable.
It confidently claims that lower temperature makes outputs more spread out and uniform. That is the exact opposite of how softmax temperature actually works.
That is incredible self-sabotage. The assistant omitted model didn't have the confusing formula to look at, so it just gave the correct textbook explanation.
Exactly.
Okay, so full context bloats our API bills, slows down our infrastructure, and actively poisons our model's reasoning through context pollution. But we also know we can't just drop the context 100% of the time.
No, we can't.
As we discussed, 33% of the time the user just says, fix the second one, and the model fundamentally needs to know what the second one is. So what is the actual engineering solution here? How do we build an app that knows when to drop the history and when to keep it?
The paper proposes a really elegant solution called Adaptive Assistant Response Emission. The researchers built a lightweight classifier to predict, on a strictly per turn basis, whether the LLM actually needs the full context or if it should use the assistant omitted context.
But they didn't just use another massive LLM to make this routing decision, right? Because that would completely defeat the purpose of saving compute. You don't want to spend 10,000 tokens just to figure out if you can save 10,000 tokens.
Precisely why they used an L1 regularized logistic regression classifier. Just to give a brief refresher, L1 regularization is a technique that forces the model to ignore useless features, driving their weights to exactly zero, which makes the classifier incredibly fast and sparse. It's dirt cheap to run.
What kind of data are they feeding into this classifier to make the decision?
It uses a few key inputs. It looks at metadata, like the current round number and token counts. It looks at the prompt category. But the real heavy lifting comes from dense vector embeddings of the user prompt and the conversation history. They used OpenAI's text embedding 3 large model.
But wait, if you use a large embedding model, you get a massive vector with thousands of dimensions. Passing that into a router for every single conversational turn would still add latency.
Which is why they ran principal component analysis, or PCA, on those embeddings.
Okay, that makes sense.
PCA essentially squashes those thousands of dimensions down, capturing the most important variants. They distilled the embeddings down to just 20 principal components. So you have this tiny 20-dimension representation of the conversation's semantic meaning.
You feed those 20 features into the lightweight logistic regression model, and it performs a fast matrix multiplication to spit out a probability. Does this specific turn need the assistant's passwords? Yes or no?
And the performance of this adaptive approach is fantastic. By using this classifier, you can retain over 95% of the full context performance on those tricky follow-up questions while still drastically reducing your overall context usage across the conversation.
That's a huge win.
It keeps the context lean, avoids pollution on the standalone tasks, but keeps the memory intact for the ambiguous follow-ups.
I imagine some engineers listening might think, I don't want to bother training a regression model. I'll just write a hard-coded heuristic that says only omit context on new asks. Did they test simple rules like that?
They did, and it performed significantly worse than the adaptive embedding-based approach.
Really?
Yeah, the regression model captures subtle semantic nuances in the prompt that a simple, hard-coded rule completely misses. The learned classifier is absolutely the way to go.
It's a massive leap forward for context management, but it feels like this is just the beginning of how we optimize memory. Where does this go next?
This raises a critical question about the future of context filtering. Right now, this adaptive strategy is making a binary choice. Either keep all the past assistant responses or drop all of them. The next logical step for AI engineers is fine-grained filtering.
Ooh.
Imagine a system that doesn't just decide whether to keep the history, but identifies the specific past assistant turn that is explicitly being referenced and aggressively deletes the rest. That is where context optimization is heading.
Let's summarize the core thesis here for everyone building in the trenches. Storing every single past assistant response is an outdated default. It is a legacy design choice from the early days of chat interfaces that is actively wasting your tokens, blowing up your VRAM and KV cache, and in many cases, poisoning your model's reasoning by forcing it to over-index on its own past mistakes.
And if we connect this to the broader AI paradigm, consider what this means for the future of autonomous AI agents. We just saw that powerful state-of-the-art frontier models like GPT 5.2 can be easily brainwashed by their own previous text in a simple contained chat window. Agentic systems are constantly dumping massive, noisy execution traces, raw tool outputs, and rambling planning scratch pads into their memory loops over dozens or hundreds of steps.
They're essentially generating massive amounts of their own context.
Exactly. If models are this susceptible to context pollution, are we accidentally polluting the context windows of our agentic systems before they even take their first real action? It's a serious vulnerability in how we're architecting agent memory right now.
That is a terrifying and fascinating thought to end on. The tools we're using to give models memory might be the very things degrading their logic. If you're building with LLMs right now, go audit your context windows. Look closely at what you're actually feeding back into your models. Thank you for tuning into this breakdown for the AI Paper Podcast series. We'll be back next time with another deep dive into the research shaping the future of AI.